Swayam Prabha. Digital India. Educated India.
Good morning. Today I'll solve some problem illustrating the application of Euler equation. Let me state the problem number 1. An axial impaler is driven at 45 radian per second. The impaler works as a pump impaler. The outer diameter of the impaler is 1.5 meter, while the inner diameter is 0.6 meter. If the energy exchange for the passing fluid, that's Euler work, is 120 joule per kg, calculate the inlet and exit blade angle with respect to the axial direction when the axial velocity is 12 meters per second. Ignore the hydraulic efficiency and assume zero inlet swell for the pump. Let me solve the problem. I have drawn here the schematic of the axial flow pump where the hub, casing, impaler have been indicated. Furthermore, I have shown here the axis of rotation and a central plane which lies between the hub and the casing. And the radius of the central plane is considered here Rm. Thus, what are the data? D2, that is outer diameter of the impaler, is 1.5 meter, and inner diameter D1 is equal to 0.6 meter. Thus, I have calculated radius R2, that is D2 by 2, that's 0.75 meter. I have calculated R1, that is 0.6 divided by 2, equal to 0.3 meter. Thus, Rm, radius of the mean section at R1 plus R2 by 2, which is 0.525 meter. Furthermore, it is given as omega 45 radian per second, Euler work E 120 joule per kg, Cz, axial velocity that's passing through the impaler, about 12 meters per second. Now, if I take the circumferential section at the mean section and stretch on the plane of a paper, I'll get the aerofoils. These are the blade, and since this is the aerofoil blade, and since these are pump impaler, the flow will decelerate. Hence, W2 will be less than W1. Thereby, beta 2 will be less than beta 1, where beta 2 is the relative air angle at exit and beta 1 is equal to relative air angle at inlet. Furthermore, I have indicated here the blade speed u, and I have considered u1 is equal to u2 is equal to u here. After this discussion, let me draw the velocity triangle at inlet and exit. Here look, giving c theta 1, that is swelling component at inlet, is equal to 0, Thus, let me draw the velocity triangle at inlet. This is W1. This will be U1 or U. This is equal to CZ. So this is W1, U, and this is C1. C1 would be equal to CZ. I have drawn here. Now this angle, that is angle between W1 and the Z axis, is equal to beta 1. Here C theta 1 is equal to 0. Now, what is the exit velocity triangle? Now W2 will be less than W1 and beta 2 will be less than beta 1. If we know this, let me draw that. This is W2. Look, now W2 is less than W1 and this is U. So this is C2. This angle is beta 2 and this is alpha 2. Now if so this is U and this is C2. So W2 plus U is equal to C2. Now component of W2 in the tangential direction would be equal to W theta 2. Component of C2 in the tangential direction would be equal to C theta 2. So I trust you have appreciated the velocity triangle at exit which I have drawn over here. Now, rest are very simple. Now, U, the blade speed, is equal to omega into Rm at the mean radius. That will be omega is given, Rm I have just calculated. So if you do this product of the two, this will be 23.63 meters per second. Thus, from inlet velocity triangle, I can project tan beta 1 is equal to U by Cz. The value of U is equal to 23.63 and Cz, the value of Cz is given as 12 meters per second. Therefore, when I calculate beta, the beta equal to 63.08 degree. After calculating beta 1, I'll have to calculate beta 2. Thus, let me project all our work. E is equal to U2 into C theta 2 minus U1 into C theta 1. However, as C theta 1 is equal to 0, so this component will go. Therefore, here the Euler work E is equal to U2 into C theta 2. Equal to E divided by U2. Now E is given at 120. U2 I have calculated as 23.60. Therefore, the value of C theta 2 is 5.08 meters per second. Now from exit velocity triangle, as I have indicated here, this component of W2 is W theta 2. So beta 2 would be equal to W theta 2 divided by Cz. Now W theta 2 can be written as U minus C theta 2. So C theta 2 I have calculated just a minute before. So this is 23.63 minus 5.08 divided by 12. So beta 2 I am getting as 57.1 degree. Thus the answers are beta 1 is equal to 63.08 degree and beta 2 57.1 degree. Note that here beta 1 is greater than beta 2 for a pump impeller. Let me state the problem number 2. Here the same impeller has been taken as an impeller for turbine. Rest all the data are remain same. Thus, the statement of the problem is an axial impeller is driven at 45 radian per second. The impeller is used as a turbine. The outer diameter of the impeller is 1.5 meter while the inner diameter is 0.6 meter. If the energy exchange for the passing fluid, that's Euler work, is 120 joule per kg, calculate the inlet and exit blade angle with respect to the axial direction when the axial velocity is 12 meter per second. Now ignore the hydraulic efficiency and assume zero outlet swirl for the turbine. So here I have considered that outlet swirl is 0. Again, I have illustrated this schematic here. As before, I have indicated hub, casing, and the impeller, axis of rotation, and a plane, which is the central plane between the hub and the casing. And let the RM be the radius of the central plane. So as before, R2 is 0.75 meter, R1 0.3 meter, and thus RM is equal to 0.525 meter. And U, the tangential component of all the blade speed, is omega into Rm, that's 23.63 meter per second. Furthermore, as before, E is 120 joule per kg. Cz, axial component of absolute velocity, which is connected to the mass flow rate of the machine, is 12 meter per second. Now here I have considered the direction of rotation be the same, and as before, if I stretch the circumferential section at the mean radius, then I'll get the blade profile as indicated here. Look here, the orientation would be different than that of the pump impeller. If you consider the direction of the rotation, U is the same. Now the pressure surface is the agency for the drive of the impeller. So this is the pressure surface, and this will be the suction surface, right? So the energy will be extracted here from the passing fluid, and thereby flow will be accelerated, relative velocity will be accelerated here to W2 will be greater than W1, and thus beta 2, the relative flow angle, will be greater than beta 1, opposite to that of the compression. And here earlier I have told C theta 1 is 0. Now here I have told C theta 2 is equal to 0. The swirling component at exit equal to 0. So if I draw the velocity triangle at inlet and exit, first let me draw the exit velocity triangle, since C theta is 0 here. So this is W2 and this is U, and this will be CZ or C2. So this is C2 will be equal to CZ, and this is W2, and this is U, and this is beta 2. Now beta 1 is less than beta 2, and W1 also less than W2 here. So if I draw the velocity triangle at inlet, it will be like this. U remains same. This is the C1. Okay. Now this is beta 1. Look, now beta 1 is less than beta 2 for the turbine, and W1 is less than W2, and this is alpha 1. So this is U, and this is C1. So hope you have understood the velocity triangle for a turbine and inlet and exit, and you have appreciated that flow and the blade angle, they are conformal, and the blade profile, they are conformal. Thereby, that is what I like to say, that flow follows the blade orientation. So one can appreciate that orientation of the blade profile here will be just opposite than that of the pump. Let's start simple after drawing the velocity triangle. So first I'll calculate beta 2. So tan beta 2 is equal to U by CZ. U, I know 23.63, CZ is given as 12. So beta 2 I have calculated here 63.08. Now let me go to the Euler work E. E is equal to U1 C theta 1 minus U2 C theta 2 here for a turbine. And so this part will be 0 because C theta 2 is equal to 0. So from Euler work, I can get C theta 1 is equal to E by U, E 120, and U is 23.63. So I'll get again C theta 1 as 5.08 meter per second. Thus tan beta 1 from inlet velocity triangle W theta 1 by CZ1. W theta 1 is equal to U into C theta 1. So I can write W theta 1 is equal to U minus C theta 1. I have calculated C theta 1 here. I know the value of U, so I know W theta 1. So I have evaluated here the value of W theta 1, and CZ is 12. Thus beta 1 would be equal to 57.1 degree. So the answer is this. Note here the angle got reversed. So here you will find beta 1 for a turbine is less than beta 2 as indicated in velocity diagram. I have solved here a problem on radial flow impeller. So statement here is a pump is designed with a backward flow radial impeller having an outer diameter of 50 centimeter and an inner diameter of 25 centimeter. The pump runs at 1500 RPM. The impeller bearings are set at an angle of 45 degree at the inlet with respect to the tangential direction. Assume zero swell at inlet and neglect slip at exit. The flow velocity through the impeller is constant at 3 meters per second. The hydraulic efficiency is 85%. Calculate the value of swell at exit the heat developed by the pump, the blade angle at inlet. I always prefer to draw a schematic before numerical calculation so that I can visualize about the problem, right, physically what is happening within the impeller. Now, this is the overall impeller schematic, and if I consider streamlines or meridional streamlines, it will be like that. So it's a fully radial flow impeller. That means when the flow enters the blade, it is radial and it's coming out radial. Furthermore, it is given that backward curved vane. So I have taken another view where I have illustrated the flow passage. So if I consider this is the direction of the rotation, the vane will be curved in this direction. That is why it is named as backwardly curved, illustrated in the lectures. Now, so this is the plate passage, and I have done both the inlet velocity and the exit velocity. Now look what are the data given here. D1, that is inlet diameter of the impeller, as 25 centimeter, D2 50 centimeter, N rotational speed is 1500 rpm, beta 2 exit relative flow angle is 45 degree with respect to tangential direction. Furthermore, CR1 and CR2, that is radial velocity as is passing through the impeller, would remains constant, that is 3 meters per second. Furthermore, hydraulic efficiency also is given as 0.85. So I'll have to proceed. First, I need to draw the velocity triangle. Look here, given c theta 1, swirling component at inlet is equal to 0. Thus, following the blade curvature, if I draw the inlet velocity triangle, it will be U1 plus W1, and this would be C1, since and C1 will be CR1. So this is U1 and this will be W1. This is beta 1. What will be the exit velocity? This will be W2. This will be U2. And this will be theta 2. Because this angle has been given beta 2 as 45 degree. So this is W2. This is U2. U2 will be higher than U1. And this will be C2. So this will be CR, relative component, that remains constant. This will be alpha 2 that I have drawn over here. Okay. Now, tangential component of W2 would be W theta 2, as I am indicating here. Now, after drawing the velocity triangle, I can solve the problem. Suppose U1 is equal to pi d1n by 60. N is given as 1500 rpm, d1 convert D1 is given as centimeter to meter. If you do all these things, I'll get U1 as 19.635 meter per second. Similarly, you can calculate U2 as pi D2n divided by 60, where D2 has 50 centimeter, that is 0.5 meter, and I'll get U2 as 39.27 meter per second. Now, at exit beta 2, the value of beta 2 is given as 45 degree, right? So I can write from exit velocity triangle, tan beta 2 is equal to CR2 divided by W theta 2. Here, this is CR2 and this is W theta 2, right? So tan beta 2 is equal to CR2 plus W theta 2. Now this is 45 degree. So from this equation I can get W theta 2 is equal to CR2, the value of CR2 as given 3 meter per second. So I can evaluate W theta 2. Now let me go to the next page. Now after evaluating W theta 2, I can get C theta 2. This is C theta 2, right? If you go to the exit velocity triangle, the projection of C2 in the tangential direction will be equal to C theta 2. So C theta 2 I can write U2 minus W theta 2. So U2 I have evaluated, W theta 2 I have just calculated. So C theta 2 I have got as 36.27 meter per second. Now head developed would be H into eta H hydraulic efficiency into U2 C theta 2 divided by G, because here C theta 1 is equal to 0. Eta H is 0.85, U2 39.27, C theta 2 is 36.27 divided by 9.81. If you do this calculation, you will get 123.4 meter. Just have got head developed would be equal to 123.4 meter. Now beta 1 inlet relative angle is very simple. From inlet velocity triangle, beta 1 would be equal to C tan inverse CR1 by U. CR1 is 3 and U1 is 19.635. If you do that, beta 1 would be 8.687 degree. That's how I have evaluated the wall values that was wanted. Swell component at exit 36.27. This is I have computed here. C theta 2. Head developed H by the pump 123.4 meter. Beta 1 is 8.67 degree. Thank you for listening.